Students, welcome. Our today's topic is mass attached to spring. Look at this diagram. Here is a mass attached with a spring placed on a horizontal frictionless surface. One end of the spring is connected with a firm support, and at the other end mass is attached. We want to move this mass towards left through a distance x. What happened? We will apply force on it. This force will compress this spring and will move the mass towards left. How much force is required? It depends upon how much we want to compress the spring to move the mass towards left. Let x is the distance through which we compress the mass and we compress the spring and mass is moved towards left. Students, by Young's law, the applied force F is equals to Kx, where K is called the spring constant. Its value depends upon the nature and material of the spring that we are using. Its value is different for different springs. So, by Young's law, the force that we need is F is equals to Kx. And when we apply this force, the spring is compressed and mass is shifted from point A to point B. Now when this applied force is removed, due to elasticity, the spring will push the mass backwards towards its initial position A. Now this is called elastic restoring force, by which the mass is pushed by the spring. This force is equal but opposite to the applied force, so we denote it with small f, and its value is minus kx. Here minus means it is directed opposite to the applied force. So from Newton's second law, we know that force is the product of mass and acceleration. Comparing these two equations or putting the value of F here in this equation, we get ma equals to minus kx. On rearranging this equation, taking m on the other side, we get equation for acceleration. A equals to minus k by m into x. Students, since k is the spring constant, spring does not change while the mass is oscillating. M is the mass that also does not change. So these two terms are constant, k and m. So we say that A is proportional to minus x. It is the required condition for simple harmonic motion. So we can say that motion of mass attached to a spring is a simple harmonic motion. Again, the two requirements are there. One is the inertia and other is the elasticity. Due to elastic restoring force, spring pushes the mass backward, and due to inertia, mass crosses the mean position. These two conditions are there, so the motion of mass attached to the spring is a simple harmonic motion. Now we will derive the expressions for its time period. What is time period? It is the time in which this mass spring system completes its one vibration. We will take help from circular motion for the derivation of equation for time period. From circular motion, acceleration is equals to minus omega square x, where omega is called angular velocity and it is equal to 2 pi by t, as linear velocity is equals to distance divided by time. Students, similarly, angular velocity is equals to angular displacement divided by time period. So putting these value here, we get expression for acceleration as 4 pi square over t square, this value of omega square here. So acceleration is equals to minus 4 pi square over t square into x. It is the acceleration for circular motion. Now for mass attached to the spring, we have just calculated its acceleration is equals to minus k by m into x, where k is the spring constant, yes, and m is the mass. Comparing these two relations, one for acceleration of circular motion and one the acceleration of mass attached to spring, we get an expression like this: k by m minus k by m into x is equal to minus 4 pi square t square into x. Sum of the term will cancel each other. Negative sign will be cancelled with this negative sign. X will be cancelled with this x. We are left with k by m is equals to 4 pi square over t square. Rearranging this equation, taking t square on the other side, t square is equal to 4 pi square, m will be here and k will move on downward. T square is equals to 4 pi square m by k. Taking square root on both sides, t square square of the t will be cancelled with the root. Similarly, 4 becomes 2 when taking root, and square of pi will also be cancelled. So time period is equals to 2 pi under root m by k. It is the equation for time period of mass attached to spring. The equation shows that time period depends upon mass only. K is constant, 2 pi is constant, so we can write that T is proportional to m under root. It is the equation for time period of mass attached to spring. More the mass, more will be the time period, and slow it will move. Next is frequency. You know, the number of vibrations completed in 1 second is called frequency. And frequency is the reciprocal of time period. Mathematically, frequency equals to 1 over t. Putting the value of t here in this expression, t equals to 2 pi m by k under root. We insert this value of t here and we will get the expression for frequency. F is equals to 1 over 2 pi k by m. So since t is in denominator, so values will be inverted. F is equals to 1 over 2 pi under root k by m. It is the equation for frequency of mass attached to spring. Students, this is all about the topic. Thank you for sparing your time to watch the video. If you liked the video, don't forget to subscribe the channel. Take care of you.